Good. So, hello everyone. Mm, my topic for today is about polymer. So the scope of my topics are all about um for the introduction of polymers, the step growth, polymerization, the free radical addition of polymerization, ionic polymerization, copolymers, and other architectures, polymers, stereochemistry, and polymerization reactions initiated by metal catalysts and transfer reaction. So to start, I am your presenter. My name is Renan D. Cortez from Masbate. For the objective is to know the basic information about polymers, and at the end of the study, the learner ought to learn about the step growth from polymerization, and at the end of the study, students will learn about the ionic polymerization. So to know about the free radical addition polymerization, learn copolymers and other architectures, learn what is polymer stereochemistry. At the end of the module, we'll be able to know the polymerization reactions initiated by metal catalysts and transfer reactions, and to know what is polymer in solution. To start, chapter 1, introduction of polymers. So molecules are compounds made up of multiple types of atoms. Water is an example of a tiny molecule. So as it includes three atoms, two hydrogen atoms and one oxygen atom. In comparison to water, polymers are enormously big molecules. Polymers have unique behavior and features, which is due in part to their size. The big molecules become entangled with one another, similar to how a single strand of cooked spaghetti in a dish of pasta. Also, the lengthy polymer chains entangle and intermingle with one another. This situation can be visualized with a bowl of cooked spaghetti without the sauce, because the strands of spaghetti are knotted together. Separating one piece from the remaining ones is extremely tough. Polymer synthesis. Polymers are a class of materials comprising small repeating chemical units. The building block or the repeating unit in the polymer is called a monomer. Polymerization or polymer synthesis is a chemical reaction in which monomers are joined together by covalent bonding to form polymer structures. The length of the polymer chain is characterized by the number of repeating units in the chain, which is referred to as degree of polymerization or DP. The molecular weight of the polymer is the product of the molecular weight of the repeating unit and the um, degree of polymerization. Structure, an important microstructural feature of a polymer is its architecture and shape, which relates to the way branch points lead to deviation from a single linear chain. A branch polymer molecule is composed of a main chain with one or more substituent side chains or branches. Types of branch polymers include star polymers, cone polymers, polymer brushes, dendrites polymer, ladder polymers, and dendrimers. There exist also two-dimensional polymers, which are composed of topologically planar repeat units. Polymer's architecture affects many of its physical properties, including solution viscosity, melt viscosity, solubility in various solvents, glass transition temperature, and the size um, of individual polymer coils in solution. A variety of techniques may be employed for the synthesis of a polymer material with a range of architectures, for example, leaving polymerization. So for the chain length, it is a common means of expressing the length of a chain in the degree of polymerization, which quantifies the number of monomers incorporated into the chain. As with other molecules, a polymer size may also be expressed in terms of molecular weight. Since synthetic polymerization techniques typically yield a statistical distribution of chain lengths, the molecular weight is expressed in terms of weighted average. The number average molecular weight, or MN, and the weight average molecular weight, or MW, are most commonly reported. So nomenclature of inorganic and inorganic organic polymers are some irregular single-stranded organic polymers can be named like organic organic polymers using the rules given above, or the rules given um the following sentences. So for the polymer molecular weight distribution and definitions of MW averages, the polymers consist of repeat units or monomers chemically bonded into long chains. Understanding the physical properties of a polymer, such as a mechanical strength, solubility, and brittleness, requires knowledge of the length of the polymer chains. Chain length is often expressed in terms of the molecular weight of the polymer chain, related to the relative molecular mass of the monomers and the number of monomers connected in the chain. However, all these synthetic polymers are polydispersed in that they can contain polymer chains of unequal length. And so the molecular weight is not a single value, and the polymer exists as a distribution of chain lengths and molecular weights. For the chapter 2, the step growth polymerization. Step growth polymerization is a polymerization method in which bifunctional or multifunctional monomers react to generate um, dimers, trimers, longer oligomers, and long-chain polymers. Step growth polymerization produces several naturally occurring and some manufactured polymers such as polyesters, polyamides, and polyurethanes. To reach a high molecular weight, the polymerization method necessitates a large amount of reactant. A group of individuals reaching out to clasp hands, clap hands to form a human chain. Each person has two hands. It's equal to reactive sites. Is the simplest way to envision the mechanics of a step growth polymerization. There is also the possibility of having more than two reactive sites on a monomer, which results in the creation of branching polymers. For the polymers and polymerization reactants, prior to the early 1920s, chemists doubted the existence of molecules having molecular weights greater than a few thousand. This limiting view was challenged by Hermann Staudinger, a German chemist with experience in studying natural compounds such as rubber and cellulose. In contrast to the prevailing rationalization of these substances as aggregates of small molecules, Staudinger proposed they were made up of macromolecules composed of 10,000 or more atoms. He also formulated a polymeric structure for rubber based on repeating isoprene unit, or referred to as monomer. For his contributions to chemistry, Staudinger received the 1953 Nobel Prize. The terms polymer and monomer were derived from the Greek roots poly means many and mono means one, and meros, which means part. So there are two general types of polymerization reactions, which is the addition polymerization and condensation polymerization. In addition polymerization, the monomers add to one another in such a way that the polymer contains all the atoms of the starting monomers. Ethylene molecules are joined together in long chains. The Carothers equation. In step growth polymerization, the Carothers equation, or Carothers equation, gives the number average degree of polymerization xn for a given fractional monomer conversion, or P. This equation was proposed by Wallace Carothers, who invented nylon in 1935. So for xn, which means the average chain length in monomer units, the P is equals to n n0 minus n divided by n0, where n0 is the number of molecules present initially, and n is the number of unreached molecule at time t. P is also the measure of the extent of reaction or yield, and the high monomer conversion is required to achieve a high number average degree of polymerization. Molecular weight control in step growth polymerization. The molecular weight of a polymer is one of the most essential characteristics, since it influences rather many mechanical and thermophysical properties, including glass transition temperature, melt and solution viscosity, and mechanical strength. To mention a few, a high molecular weight is preferred for many applications. Step growth, on the other hand, can only produce polymers with high molecular weight if three key conditions are met. First, the two dysfunctional monomers AA and BB must be blended in perfect stoichiometric balance. This equilibrium is provided by the hydroxy acid. The second, monomer impurities that can react in step growth must be reduced to a bare minimum, as even a tiny amount of a monofunctional reactive component can cap the expanding polymer chains and stop them from forming. Monomer impurities that can react and terminate step growth have to be kept at an absolute minimum, because any trace amount of monofunctional reactive compound will cap the growing polymer chains and thus reduce the molecular weight. However, stringent purification of the reactants is often difficult and adds cost to the final product. Lastly, the step growth polymerization has to be driven close to the completion to a very high yield without any side reactions. For kinetics of chain polymerization, alkenes polymer, polymerize in a totally different way than monomers that go through condensation processes. Polymerization of alkenes entails a chain reaction, whether it occurs via an anionic, cationic, or radical process. We'll look at the treatment of radical chain polymerization to see some of the elements that influence polymerization rates, because radical chemistry is a famous example of chain reaction. So for the third chapter, introduction of polymers. So for free radical polymerization, FRP, so sorry for that. So to continue, for the third chapter, which is the free radical addition polymerization. The free radical polymerization or FRP is a polymerization process that involves the sequential addition of free radical building components to produce a polymer So free radicals can be produced through a variety of methods, most of which require independent initiator molecules. The initiator is the polymerization initiator, a source of any chemical species that reacts with a monomer or single molecule that can form chemical bonds to form an intermediate compound capable of linking successively with a large number of other monomers into a polymeric compound. The most widely used initiators produce free radicals or reactive atoms or groups of atoms that contain odd numbers of electrons. Examples include peroxides and Aliphatic compounds used to polymerize vinyl chloride, methyl methacrylate, and other monomers. So in addition, polymerization monomers react to form a polymer without the formation of byproducts. Addition polymerization usually are carried out in the presence of catalysts, which in certain cases extend control over um, structural details that have important effects on the properties of the polymer. So one of the most useful and lucrative fields of chemistry ever discovered in the recent years have seen a tremendous increase in research into this area once considered a mature technological field. Free radical synthetic polymer chemistry is tolerant of diverse functionality and can be performed in a wide range of media. Emulsion and suspension polymerization have been established as important industrial processes for many years. More recently, the green synthesis of polymers has diversified from aqueous media to supercritical fluids and the fluorous biphase. Free radical polymerization of low molecular weight monomers in the presence of a cross-linking agent can be used to produce hydrogels. Free radical polymerization is frequently used to prepare hydrogels for bio applications. This is a very efficient and widely used method and results in the rapid formation of the gel even under mild conditions. The amount of crosslinker used controls the characteristics of hydrogel and the swelling of hydrogel in particular. Prominent natural um, sorry. The amount of crosslinker used controls the characteristic of hydrogel and the swelling of hydrogel in particular. Prominent natural hydrogels that can be chemically cross-linked by this technique are HA, dextran, and chitosan. This method involves the chemistry of typical free radical polymerization, the main steps being initiation, propagation, chain transfer, and termination. In the initiation step, visible, thermal, ultraviolet, or redox initiators form free radicals. These radicals, upon reaction with monomers, convert them into active forms, which then react with further monomers, and so on in the propagation step. Termination is brought about either through chain transfer or through radical combination developing polymeric matrices. This method of hydrogel preparation can take place either in solution or in bulk. So these are the steps in chain growth polymerization. First is the chain initiation step is the reaction to generate a chain carrier or intermediates such as radicals and ions in the chain propagation and chain polymerization. Second, chain propagation step is a step in which an active center on the developing polymer molecules adds one monomer compound forming a new polymer molecule that is one repeat unit longer with a new active center. The third is the chain transfer step, is a key step in which the active center of polymer A receives an atom from B compound and gets terminated. Then the molecule forms an active center. In this step, the active point only shifts to another molecule and does not disappear. This step may occur in the coordination, ionic, and free radical polymerizations. The last one is the chain termination means that the active center disappears in chain polymerization, causing the termination of chain propagation. Or the chapter 4, ionic polymerization. Ionic chain polymerization is a chain growth reaction where the active center is charged, either negatively leading the anionic polymerization or positively charged leading to cationic polymerization 1 to 13. Anionic polymerization is essentially limited to those monomers bearing electron withdrawing groups, whereas cationic polymerization to those polymers possessing electron releasing substituents. Ionic polymerization requires stringent reaction conditions, including high monomer purity, including high monomer purity. In addition, the polarity of the solvent greatly influences the mechanism and rate of polymerization. The kinetics of cationic polymerization of olefins differ from free radical and homogeneous anionic synthesis of high polymers in that the cationic systems have not so far been fitted into a generally used kinetic framework involving fundamental reactions like initiation, propagation, and so on. To explain the reasons for the peculiar problems with the cationic polymerization, we will, however, postulate a conventional polymerization reaction scheme and show where its inherent assumptions are questionable in cationic systems. For the fifth chapter, linear copolymers and other architectures, the difference in water uptake between polymer like structure, random and multi-block copolymer is due to the intrinsic distribution of sulfonic acid and structural difference. The homopolymer-like structure provides a more uniform distribution of sulfonic acid groups, which reduces the local sulfonic acid concentration, while multi-block copolymers have self-assembled morphology, where the sulfonic acid groups aggregate in the hydrophilic domains. Grafting polymer architecture, on the other hand, appears to have much less impact on water uptake. So for the chapter 6, polymer stereochemistry, stereochemistry of propagation. The stereochemistry of the propagation step could be studied by the overall chain microstructure or in more detail at the model level of beta substitute styrene or sterines. Comparison of propagation with the electrophilic addition reactions requires application of the correct models of carbonium ions because the hydration and addition of of halides proceeds by a different mechanism. Stereochemical studies indicate that the lifetime of the carbonium ion derived from the alkene is long enough for a conversion to a less sterically hindered isomer and for eventual recombination with the fluoride which produces a Z product. The trans the transisomer hardly converts to the more hindered isomer and gives a high proportion of the E product. The classical reaction scheme accounting for the observed toxicity is based on the assumption of front side attack in more polar solvents and backside attack in less polar solvents. The high proportion of front side attack in CH2Cl2 solvent is surprising. What prevents the backside attack? The substituent at beta C atoms seem to be too far from the approaching monomer to hinder the backside attack. The explanation could be based again in the interaction with an adjacent aromatic ring. So, thus, instead of the extended zigzag conformation, the real chain is perhaps twisted to maximize the interactions between the Y aromatic ring and the carbonium center. The presence of the aromatic ring in the intermediate neighborhood and the relatively weak interactions with the anion may facilitate the front attack, which apparently requires an unfavorable separation of counter ions. For the chapter 7, polymerization reacts initiated by metal catalysts and transfer reaction. The polymerization reaction proceeds by an ordered mechanism which consists of the following steps. For 53, 54, A template DNA or DN containing N nucleotides binds the polymerase or E, and DNTP is selected from the pool of nucleotides to form a ternary complex. The polymers undergoes a conformational change to catalytically active form E. And for the fourth step, chemical catalysis takes place at a rate faster than the conformational change. A second conformation change occurs at step 5. The PPI product is released from the ternary complex, which is for the step 6. And for the step 7, either the polymerization product DN plus dissociates from the polymerates or translocates to start new cycles for steps 2 to 5 of polymerization in the presence of DNTPs. Anionic polymerization reactions. Polymerization reactions of two oxytanon, and 4-methyl or T-oxytanon for beta-propiolactone and beta-butyrolactone, respectively, have been and continue to be intensively studied. Many mechanistic studies of anionic polymerization reactions have been reported in the period 1983 to 1993. Polymerization systems. Polymerization reactions are carried out in the vessels or reactors, generally with the application of heat and with the addition of different substituents depending on the phases that exist and the forms of the medium. Polymerization processes are classified as homogeneous and heterogeneous systems which consist of the different techniques given below. So homogeneous polymerization systems, all chemicals are in one phase and homogeneously dissolved in the phase. There are either bulk or solution polymerization processes. Bulk polymerization, in these polymerizations, there are only monomers and initiators in the reaction medium. These processes are generally used in the production of condensation polymers in which the reactions are mildly exothermic, of low viscosity, and therefore mixing, heat transfer, and control of the process is easier compared to chain polymerization of vinyl polymers. For B, solution polymerization. Monomer and initiator are dissolved in a solvent and the reaction takes place in this solution. This approach can be used for addition or condensation polymerizations since the medium does not get to viscous, which makes mixing, heat transfer, and control of the process easy. On the other hand, it requires purification and removal of the solvent. Heterogeneous polymerization systems, there are more than one phase creating a heterogeneous media for the monomer, polymer, and initiator. For gas phase polymerization, in these systems, the monomer is in gaseous state and the polymer formed is either in liquid or solid form. Ethylene polymerization is an example for gas phase polymerization. Precipitation polymerization, it is also similar to box or solution polymerization, but the polymer formed precipitates as soon as it forms because the polymer is not soluble in its monomer and the solvent of the monomer is not a solvent for the polymer. For C, solid phase polymerization. Some solid crystalline olefins or cyclic monomers polymerize by solid state polymerization. In these systems, polymerization generally starts with exposure to electromagnetic radiation such as X-rays or gamma rays. For D, suspension polymerization. Organic phase containing the monomer and the initiator is dispersed as droplets in the aqueous phase containing stabilizers in order to increase the viscosity and keep the suspension stable as cellulose or polyvinyl alcohol. The initiator is soluble in the monomer phase. In the droplet, the polymerization mechanism is very similar to bulk polymerization. The size of the droplets is in the range or 0.01 to 0.5 centimeter, and the polymer forms as solid particles of this size. So that is it for my report. Thank you very much.